We present Learning to Factorize and Relight a City. Our work explores a new source of unsupervised data and how such data enables powerful relighting capabilities. Imagine that we want to visit any of these corners of New York City on a random day like July 9th, 2011. We could search all of social media to see if anyone uploaded a picture of their 2011 summer trip to Columbus Circle or the Flatiron Building. But this wouldn't be particularly scalable if we wanted to pick a different day. And it would almost be certainly impossible for a truly nondescript corner of New York that no one would bother to capture. So how can we virtually visit these corners at any point in time? For this, we turn to Google Street View Time Machine as a source of imagery. Because these images are captured by cars that repeatedly drive through a city, they contain the same locations captured over multiple years. The advantage is that by the sheer scale of Google Street View, even the most random corners of New York can be visited, allowing us to collect data at a truly world scale. However, this data is still incredibly sparse and irregularly sampled, so we still can't pick any date to visit. How can we fill in the missing entries in the time machine? Well, for one, we know that buildings tend to last a long time, so if they can be seen in one picture, then they're likely persistent across all other pictures. But the more important question to being able to visually travel in time is learning what things change between views and how we fill in the missing entries that are changing. For instance, there are many things that change between views. For one, the range of potential illuminations is complex. On clear days, the sky might be a bright blue. In the wintertime, you might predominantly see cloudy days, and in the early evening, the sun begins to exhibit qualities of the golden hour. Other things like the sun and clouds lazily drift through the sky. What we can conclude is that there's a very natural way to separate the visual world of the city: the permanent parts of the world like buildings which will persist over the years, and the temporally varying things like cars, clouds, and illumination. In this work, we primarily focus on illumination as an important temporally varying property. Once we have this disentanglement, the act of visually traveling in time is a matter of changing the temporally varying things to match the desired point in time while keeping the permanent elements the same. For example, we can take the scene on top and change the time so that the sun appears in a different part of the sky. The fact that we can manage to get a realistic looking result is proof that we did a good job separating the physical buildings from the illumination effects. Next, we can also choose to try and edit properties of the sky, such to imagine what the top scene might look like in the evening or in the wintertime. Finally, with a disentangled permanent representation, we can also modify a scene by duplicating a building. If we just copy-paste the pixels of the building from here to here, it looks pretty terrible as there are obvious edges where the building was pasted. But if we instead form the copy in the permanent factor, we get a nicely blended result. But how do we learn this disentanglement? In a given image, we don't know what is permanent and what is changing. For example, let's focus on this patch. The appearance of this patch is partly the result of permanent texture of the building, and partly a result of the shadow caused by the sun. But they are all intermingled together, so separating them is a hard problem. Because Google Street View Time Machine is a collection of imagery of the same place across time, we can observe the same building under a wide variety of illuminations. So even if it's entangled in one view, we can cross-reference with another view where it's clear. Because our goal is to learn this factorization for any possible scene, we need to construct a dataset with as much diversity as possible. And I mean a lot. To learn our disentangled factors, we collect a massive dataset of time-lapse videos from Google Street View Time Machine, spanning almost 10 years of New York City. We identified 100,000 locations around New York City which had at least 8 panoramic captures. For each panorama, we collected date, time, and the latitude-longitude of the location. However, our model only uses the image data to learn its factorization. We note that everything here is completely unsupervised. No human annotation was necessary to assemble this data. So our goal is, given an input stack, to learn to separate the varying factors from the permanent ones. Note that these are learnt embeddings. Let's start by looking more in detail for the temporally varying factors. Since each image in the time-lapse comes from a different point in time, we will predict one temporal factor per image. We further split the temporal factors into 2 subfactors. The first is a feature vector, which is most similar to a learnt style embedding, which encodes properties about the illumination. The second is an explicit representation for sun azimuth that is naturally discovered by the factorization model. Next, we'll look at the permanent factor. The permanent factor is shared across the stack as each image is of the same underlying scene. The permanent factor encodes the properties of the scene that is consistent across time. Our network predicts a feature map for it. So what do we require from these features? Most importantly, we'd like them to generalize across the dataset. We want to be able to apply our disentangled factors for not just New York City time lapses, but even for data of a single image for which we don't have a time lapse, or perhaps images from another city like Paris. So far, we've discussed the disentangled factors, but not how to actually learn them so that they encode these different temporal properties. For that, we revisit a 40-year-old concept of intrinsic images. Intrinsic images are based on the physics behind the image formation. In particular, an image can be decomposed to two images: reflectance, which captures the physical properties of the scene like texture, and shading, which are changes in the image as a result of illumination. This makes intrinsic images also a disentanglement between permanent and varying. The reflectance encode properties of the scenes that won't change, but if you pick a different time of day, you will get a different illumination. One crucial thing missing from conventional intrinsic images is how this disentanglement can be applied across different scenes. For instance, if I wanted to apply the cylinders shading to a pair of cubes instead, an intrinsic image decomposition couldn't possibly give us what a pair of cubes looks like with the cylinder's illumination conditions. Nonetheless, we can take inspiration from the works in intrinsic images because they have the temporal property we desire to learn in our factors. So to get these embeddings to encode permanent versus varying, we also learn to decode intrinsic images from our embedding. Finally, we can reconstruct the time-lapse stack from these decoded intrinsic image components. This allows us to train the model in an end-to-end manner, where the network naturally learns to factorize the image into varying and permanent factors. One thing that people may notice that we've ignored is alignment. Here, we show the average of one of our time-lapse stacks we collected. It's blurry because the images within a stack are misaligned, and if we don't solve for alignment, the factorization model could wrongly believe that the buildings move slightly and are actually a time-varying thing. How can we approach this? We could try warping each image to minimize the pixel inconsistency of the RGB input image directly in advance. But this doesn't work because there are too many things changing. This is a chicken and egg problem. We want to align stuff so we can factorize the permanent parts correctly, but we can't align the time-lapse because the images have temporally varying things. The insight here is that we want to ignore the time-varying parts and focus on aligning the permanent parts. Our solution is to warp and minimize the inconsistencies within the permanent stack reflectance. We do this while simultaneously training our factorization, such that as factorization improves, alignment becomes easier. As an example, here's the computed reflectance of a city scene from New York before training starts. As we train, we alternate between improving alignment and improving factorization, such that by the end, the scene has been warped into alignment and we have discovered a clean reflectance with a gray sky that is suitable for relighting a wide variety of illuminations.
But Andrew, did you just say relighting?
So far, everything has been about learning a factorization of city scenes. We still haven't discussed how we can fill in the time machine nor virtually visit a scene at any point in time. At the end of the learning this factorization, we have a couple of different things available to us. We have our disentangled factors for this scene that are important for reconstructing the input by decoding to its intrinsic image components. The important thing is to preserve the permanent parts. In this case, reflectance serves this purpose by preserving the texture and color information of the scene. Now let's say we want to visit the top scene at the time when the bottom scene was taken, or vice versa. With our disentangled factors, we have a time-varying representation that captures the essence of time-varying property. If we were to swap the representations, we could then decode a shading image of the top scene with the illumination of the bottom scene. This shading image, when combined with the reflectance, now reconstructs a scene with the new illumination. As you can see, we've managed to successfully imagine what each scene looks like with the other's illumination. This is how we can fill in missing entries of Google Street View Time Machine. In addition, we can also use this framework to arbitrarily relight a city scene from a single image of an entirely different continent like Europe. Please visit our website, and thank you for your attention.